So today's class we are going to study about the time domain filters. So in the time domain filters, if you have we have two different types of classification. One is synchronized averaging, another one is moving averaging. So we are going to study the synchronized averaging now. So before going to study the synchronized averaging, let us see what is meant by time domain filters. So here, time domain filters are the filters which are realized in time domain, and the advantage is here the spectral characterization of the signal and noise is not at all required. So directly we can apply, that is in the time domain itself we can do the processing of the signal, and the time domain processing it is faster than frequency domain filtering. So now let us study about the synchronized averaging. So here, sometimes the linear filters, it will fail when the signal and the noise spectrum overlap. But in the synchronized averaging process, here we can separate the repetitive signal from the noise without distorting the signal. So how we are going to achieve this? So example, when you take the ERP signal is event related potential signal, and when you take the SEP, is somatosensory evoked potential. So in that case, you are going to apply the stimulus over the skin. Example, a hot water, it is placed over the skin. The skin that is near to it, it will be the skin will what it will react. That is, we are taking the hand away from the hot water. So that time, if you see like that, when you give the stimulus, and that time how your brain respond to that particular stimulus, that we call it as SEP. So like that, at each instant of time you are applying the stimulus and getting the response. So like that, 4 or 5 signals you are getting at different instant of time. Then you are going to arrange the signal, align the signal properly, and then average those signals. So if you do, whatever the noise which is present, it will be eliminated when you perform the averaging. So in this, the random noise will be zero, having zero mean, and it is uncorrelated the signal. So when you average the signal, we can able to improve the signal to noise ratio. So to explain this, let us consider yk of n is a one realization of a signal, and k equal to 1 to m represents the ensemble index, and n equal to 1 to n represents the time sample index, and m represents the number of copies or events or epochs or realization. So when we consider the number, n represents the number of samples in each signal. So when you consider the realization of a signal, it is represented as yk of n equal to xk of n plus k of n. Xk of n is a one original uncorrupted signal, k of n is a noisy signal. So if for instant of time, so we have m copies of signal. We have more number of signals. That means we have, in case of ERP itself, we have applied the stimulus and getting the response. So we have more than 5 to 6 signals. We have to average it. So when you average it, it will be represented in terms of summation k equal to 1 to m yk of n equal to summation k equal to 1 to m xk of n plus summation k equal to 1 to m beta k of n. So the first term represents a signal which is uncorrelated with the noise, and the second term represents completely noise. So if the repetition of the signal is identical and if we properly align it, then the equation becomes summation k equal to 1 to m xk of n equal to m into x of n. Here m is number of copies. And if the random noise is 0 and having 0 mean, so then the second term will be tends to 0 as m increases. So finally we will be getting the expression as yk of n summation k equal to 1 to m yk of n equal to m into x of n. So the RMS root mean square value of noise in the average signal is given by root of m into sigma neta. So the signal to noise ratio of the signal increases by root m. So for larger number of epochs or realization average, better the signal to noise ratio. So the synchronized averaging is a kind of ensemble averaging. So when we see the algorithm description of the synchronized averaging, first of all we have to choose the number of realization of signal, and we need to determine the reference point for each realization, that is a trigger or stimulus occurs in the ECG. Then we have to extract the signal corresponding to the events and align those signals, and finally we need to divide the result by number of events added. So if you see this particular signal, this is an event related potential, visually evoked potentials. Um, which is taken by applying the stimulus. Example, a flash of light or something, it is applied to the eye. How the brain responds, that is called visually evoked potential. So we obtained four different signals by applying four different stimulus. All those signals are aligned and then averaged. So after doing this averaging, you will be getting a single signal with the noise will be getting reduced. Now the second signal is ECG signal with some noise is there. So when you apply the cause correlation technique with the template, the noise will get reduced and finally you will be getting a proper ECG signal. So here, according to the template matching techniques, the normalized cross correlation coefficients, it is calculated by this formula. Rx by of k equal to this one. This is a formula to calculate the normalized correlation coefficient. Then when you use the template, we call it as x. K is the time index. So when you see initially the signal is corrupted with the noise here, and for cycle number 3, for cycle number 5 also, and after 11 cycles when you average it, you are getting the noise is getting reduced, only the signal is extracted. So thank you.